Welcome, ladies and gentlemen. I'm Sarah Jones Nelson. It is a great pleasure to introduce to you Sir Roger Penrose for the third Lewis Clark Van Exum Lecture on the new physics of the universe entitled Fantasy. If ever it was your fantasy to be cited 34,000 times on the web, you have it realized in Sir Roger. But fantasy here refers to the subtler English sense of reality and uses of imagination in historical reconstruction, in this case from evidence of the most distant past observable, the Big Bang, the creation of space-time, and the early formation of structures like matter, light, galaxies, stars, and our island Earth. The philosophical questions Penrose raises today have intrigued philosophers of science from Aristotle to Kant, Wittgenstein, Einstein, Schrödinger, and Heisenberg. The questions themselves are guides to rigorous skepticism towards standards for verifying the fundamental laws of nature that appear to have caused the early universe to evolve as it has. Penrose echoes the quintessential skeptic, Richard Feynman, in asking, what do you care what other people think when you think about physical reality? The idea is to recognize what Nietzsche and Popper called herd mentality, which is something like unreliable gossip, and to be confident in risking original, testable applications for string theory, for instance, or for newly established data from the cosmic microwave background. Some of the deepest questions Penrose is asking today concern causation. Do we have a satisfactory model of the early universe? To what extent does inflationary cosmology agree with current observations? And does it violate the second law of thermodynamics? Does present quantum theory realistically account for Schrödinger's measurement paradox, or will we need a new physics welding together gravitation and quantum theory to do so? How do we objectify the results of quantum mechanics when the role of the observer is so crucial? Does the incompleteness of quantum theory call for modification at the initial state of the universe? What is the status of the anthropic principle and the teleological explanations of astrophysical phenomena? Roger Penrose has made truly outstanding technical contributions in mathematics and physics. He would not call himself a philosopher, but he raises fundamental philosophical questions at a deep level. It is our privilege to hear him speak today. Sir Roger.
Do you think it's possible to move the table there?
Where do you want it?
Just in the middle. In the middle. Yeah.
In the middle?
Yeah.
Here's some water. Thanks.
Thank you. Well, the title of today's lecture is Faith. No, it isn't, is it? Fantasy. The faith was last time. Fantasy. One of the issues that was relevant to the previous two talks was whether the title was in some sense justified. I mean, string theory is undoubtedly a fashionable theory, and the question is its fashionable status justified, or does its perhaps it's too fashionable? And again, faith is the quantum mechanics is something which we certainly have good reasons to believe in at the level of small-scale phenomena, but does that allow us to believe something on a very large scale? Well, today I want to talk about fantasy, and okay, you might say, well, fantasy, that's a bit too anything which purports to be a scientific theory. If you call it fantasy, that usually means that you're not going to take it seriously. But the subject I want to talk about today is one in which there is something very extraordinary going on, or I should say was, and the question is, to what extent are we justified in adopting points of view or theories which are, in one respect or another, pretty fantastical? Well, that's the question I want to address, really. Now I'll have to figure out how to turn this on, which is probably beyond me. Oh, that's it. Here we are. And what I want really to start talking about is something Sarah mentioned. Well, she mentioned a lot of things, so it doesn't tell us too much. But it's the second law of thermodynamics, which is something which seems to be very fundamental to physics as we understand it. What does it tell us? Well, it tells us, for example, that if we have a hot body and a cold body, and we connect them with some kind of heat-conducting link, then the hot body gets cooler and the cold body gets warmer until the temperatures are equal. Actually, this assumes that the specific heats are positive in what I said here. What the basic point is that heat will flow from the hot body to the cold body, and in doing so you expect the hot body to get cooler and the cold one to get warmer. And that's only the last part requires this specific heat thing, so don't worry too much about it. Happens to be the case that black holes tend to go the other way around, but that's not so important with what I want to say here. Anyway, this is a fairly obvious commonplace thing, and here I have a cartoon of it. Here's a hot body and a cold body, and you join them up, and in doing so they both become lukewarm, is the idea. Well, more generally, the entropy of a system increases with time, or it could just stay constant. The entropy is basically a measure of disorder. So this is a rather pessimistic statement. It's saying things are getting worse in a certain sense all the time. I'm going to qualify that later, but that's the way some people interpret it anyway. The disorder increases. Well, that's quite obvious when I'm at work, but I mean, it's not always so obvious as that. But I want to point out a nice quote from Eddington, quite a famous one. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, those experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can offer you no hope. There is nothing for it but to collapse in deepest humiliation. So this is giving you some feeling for the importance and even necessity of this very fundamental law of physics. In fact, there's a similar comment by Einstein. I haven't got the reference to that explicitly here, but Einstein made a comment of the same ilk, same general nature as this one here. So that's actually, I've got two of these projectors this time, so I suppose I could put one of these over here, and you can, I suppose this one turns on the same way as that one did. Yes. Right. There we are. Except the writing may be a bit small. Let me say a little bit more about the second law. Here we have some cartoons of a glass of wine sitting on the edge of the table, and let's suppose it gets nudged a bit, falls off, the glass smashes, and the wine gets absorbed into the carpet. And this is something that you wouldn't expect to see happen in the opposite direction. So if this is number 1, that's number 2 and number 3 in a temporal order. Well, that's fine, but if somebody told you this was 1 and that 2 and that 3, or you wouldn't believe them. So this is a sort of commonplace illustration of the second law. The entropy is getting larger as you go in the right direction. And that is the time in, let me say more about that in a minute. That is the direction of time increasing. What's a little bit strange about this is meant to be a Newtonian picture, and so you're thinking about the particles involved, and the dynamics of Newton is something which is completely symmetrical in time, So you might argue, why doesn't it ever go the other way? If it'll go this way, then it's equally in accordance with Newton's equations that it should go the other way. But you just never see it happen the other way. Well, I want to give you some understanding of why we expect things to go this way. First of all, I should be a little bit more precise about what we mean by the entropy of a system. The entropy is increasing here, but what is entropy? Well, this is really the idea due to Boltzmann. It's a very powerful and important idea. First of all, I want you to imagine what's called phase space. Well, what is phase space? I've tried to draw it here, but not very adequately, because it's supposed to represent, any point in this space represents a state of this system here. It, in fact, tells you where every particle is located and which way it's moving. So you have 3 coordinates for the position of each particle and 3 more for which way it's moving, or the momentum of the particle. And that gives you 6 coordinates for each particle. So if you have n particles, then there are going to be 6n coordinates to describe a point here. In other words, 6n dimensions. And that could be an incredibly huge number, even just for a little tiny thimbleful of air, say. The number of molecules in there would be pretty enormous. And so that the dimension of this would be very huge. Now, what do you do? Well, what you have to do is you coarse grain the space. Now, that means that you draw some little boxes or bubbles around those regions of phase space which look more or less the same. Now, that's a bit vague, but it turns out the vagueness doesn't matter too much. What you do is you take sort of macroscopic parameters, things that you could measure, for example, the temperature and so on. It may be the temperature in different places. Macroscopic quantities, so you don't need to know where every single molecule is, every single atom is. Perhaps you don't need to know that. What you need to know is maybe some crude overall parameters which will be good enough for practical purposes. And in one of these boxes or bubbles, you assume that everything is more or less the same from that point of view. So from these macroscopic parameters, within one of these regions, they're pretty well distinguishable, or the states that they describe. And then what you do is you take the logarithm of the volume in phase space. This is a 6n dimensional volume, but never mind. You take the logarithm of that, and then you multiply it by a thing called Boltzmann's constant. This is Boltzmann's formula. I should say that he never introduced that k. Like so many things in history of science, the names attached to things aren't necessarily the names that Boltzmann wasn't quite interested in sort of details of units and that sort of thing. He was more interested in general principles, so he didn't care about that. But it's very appropriate that this is called Boltzmann's constant. Okay. Now, one thing I should say about this is that this picture, as I said, is not very accurate, because the number of dimensions looks as though it's 2 there, but it's really some huge number. And more important is that in these large numbers of dimensions, the volumes that you're talking about can vary absolutely enormously. So although I've just drawn some of these, a few times as large as some of the others, you have to bear in mind that the difference in the sizes of these volumes is absolutely stupendous. Now, let's imagine you have, say, this configuration here, represented by some point. Well, it would be, say, this point here, in some pretty small box. And the evolution of that, according to Newtonian dynamics, would be that this point wiggles around in this space somehow. Let's not worry too much about it, how it wiggles. Let's suppose it's fairly general. If it's in a small box, it's surrounded by other boxes, in general, which are much huger than it. And when it gets into a larger one, there's pretty well no chance it's going to find the small one again. And so the entropy, which is the logarithm of this thing, has gone up. And then it's likely to find itself into another huger box, and so on. And that's the understanding. Second law looks pretty obvious from this point of view. because these boxes are so much huger than the ones around it, that, I mean, when it gets into a big one, it's not very likely to find the smaller one it came from, and that sort of thing, and others of the same size. So the entropy increases in this way. In fact, that's a very good sort of partial understanding. And I'll explain what I mean by partial understanding in a minute. It gives you the predicted value very well. That is to say, well, I'll cover that up, in fact. Let's say, suppose you know the value now of the entropy. Entropy is the S that's going up the picture here. If you know the value now, it gives you a good prediction of how this will increase in the future. That's more or less, well, I've only given you a very crude argument here, but it's more or less the reason that entropy goes up in the future. But then there seems to be a catch here, you see. As I said before, Newtonian mechanics is time symmetrical. So how is it you seem to have deduced the time asymmetrical law from some completely time symmetrical ingredients? Well, you see that there is actually a puzzle here, because instead of trying to predict, suppose you try to retrodict. Suppose you try to ask the question, if you got the system now and you know what it is, what's the most likely way it could have reached that configuration? And we can ask that question for our system here. So let's say this is the state you're talking about, and you say, how likely is it that what's the most likely way it could have got there? Well, you apply the same argument, and you just do it in the past. And what it tells you is the most likely is that it started like this, then it went to this, and then that. The most likely way of getting from here was that you had a mess on the floor, and the glass sort of jumped off the ground and assembled itself, and the wine kind of collected itself in, and it settled itself delicately on the edge of the table. And that's exactly what this argument would give you. So there is something funny. That's the wrong answer. We know glasses don't do that. But nevertheless, if you simply take the reverse of the argument I've just given you, naturally enough, you get the symmetrical argument in the opposite direction. And this tells you the retrodiction, assuming that this thing is just wiggling around, if you like, randomly, then it should do this. But we know that isn't what happens. When we look at things in the real world, we don't find that. What we find is something else. And what we find is something more like this. That it went down, down and down into the past. And the reason, if you like, that it went down is, well, when you go into the past, things seem to have a teleological kind of character to them. It looks as though there's something dragging it down. And that is that it had to have, each time, you see, if we believe in the second law, it tells you that each time the entropy must have been smaller in the past, and therefore it finds its way into a smaller region, and therefore into a smaller region, and a smaller region, and a smaller region, until you work your way all the way back to the Big Bang. In fact, just quite sort of obviously, the entropy here must be at its smallest value. And so if you want to be consistent with the second law, and Eddington told us that we better not try and do anything else, then that means the Big Bang entropy must be much smaller than anything else. Well, I'm going to try and give you an estimate of that shortly. But anyway, let's just see what it says here. To ensure that the entropy continues to go down in the past, we need an enormous constraint on what happened at the Big Bang. Well, let me just say a little bit more. I've said the space-time geometry. Now, why do I say that? That's because, according to modern cosmology, the matter itself was in what's called a thermal state in the early stage. If that weren't the case, we would not have agreement with observation. Well, let me put this one on this side. Notice that I have in this picture the largest volume there is what's called thermal equilibrium. That's this region here, and it's completely swamps the others. It's far larger than all the others put together, and if you just chose a point at random, you'd almost certainly find yourself in thermal equilibrium. This what people find is, as far as the matter is concerned in the early universe, it seems to have been in thermal equilibrium. This is a sort of paradox, you see. How is it that the matter in the early universe can have been in thermal equilibrium, and then that represents a maximum entropy state, and from there on it went on up. Well, it couldn't have gone up if it was at maximum to begin with. So there's something being left out here. People used to think, well, what's been left out is the fact that the universe was pretty small in those days, and maybe there wasn't much room for a big entropy. But that argument doesn't really work when you take into account that really you've got to consider not just the universe as given, but according to Einstein, the geometry of the universe is a dynamical thing. It's something you should consider along with all the other fields. So you have to put that in as well, not just say it's something given. And so you haven't answered the question just saying it's small, because that's one of the parameters. So you have to say why. Well, it isn't actually a question of it being small. There's something much more subtle going on. But the general statement is that it's not just the matter that we have to consider, but the space-time geometry. And the space-time geometry represents the gravitational degrees of freedom. And what we say then, that what's so special about this initial state, is somehow that the gravitational degrees of freedom weren't thermalized. They weren't part of its thermal state. Somehow they were aloof from it all. They were just sitting there waiting to come into play later. Now, I want to try and estimate the size of the contribution from the geometry. How enormous, in fact, was... Well, this is one of the troubles that often when one was talking about mathematics of Big Bang and so on, you say is, you see. How enormous is this constraint? But then, of course, that was a long time ago. It's not now, so was may be the right word, and sometimes it gets very confusing. Okay, well, let's try and say something about that. To estimate the size of the total phase space volume, well, let's say for some given amount of matter that's in the universe, and let's take for that amount of matter that which we actually see in the observable universe. And according to standard cosmology, you can only see out to a certain distance. The universe might continue beyond that, but there is a distance, and that takes us out to the edge of what's called the observable universe. There'll be a little bit more about this sort of thing later on. And in fact, you might say, how much matter is there in the observable universe? Well, actually, I'm going to use a figure which is a little bit out of date, perhaps, because a lot of the matter in the universe seems to be in a form that we don't directly see. Well, there's some mysteries about all this. So let's, in fact, use this old-fashioned number, which is the number of baryons, that means protons and neutrons, in the observable universe. It's not going to make a huge difference. Well, it is actually going to make a huge difference for the actual values that come out, but not a huge difference for the qualitative arguments, because they don't matter too much in exactly what these figures are. But let's take the mass under consideration to be that in 10 to the 80th baryons, which is sort of roughly the scale of how much would be in the observable universe. And now we want to ask, what is the maximum entropy state for this matter? Well, what's very remarkable is that we can actually have a stab at working this out by using a famous formula which is known as the Bekenstein-Hawking formula for the entropy of a black hole whose mass is m. The letter S seems to be the thing used for entropy. I was using it up there. And this is the black hole entropy. BH you can think of as black hole, or you can think of it as Bekenstein-Hawking, if you like. It's one of those accidents that they happen to be the same letters. And this is the formula for it. This is Boltzmann's constant, the speed of light, gravitational constant. And that's Dirac's form of Planck's constant over 2 pi. And A is the area of the black hole's horizon. So this is a very remarkable formula. And you can actually work out what this A would be for the black hole for which it's the maximum. The spherically symmetrical black hole, and it's 16 pi g squared over c h cross times the square of this mass. Now, if you put all the mass in the observable universe into a black hole, that's a good stab at the maximum entropy. In other words, this is telling you if you take the logarithm of that, I should say, I'm so sorry, the other way around, the entropy is a logarithm, so that means you take the exponential of that, that gives you the size of this total available phase space. I've called the volume 10 to the 10 to the 123. Now, I think in my first lecture I used as an example something where I said, well, it should really be e to the 10 to the 123 because the logarithm that you're using here is actually a natural logarithm, and when you go the other way, the inverse of the natural logarithm is the exponential, but where you put an e there. But as I pointed out last time, it doesn't make a huge difference with numbers this big. In fact, what's more, I haven't even written down any units here. That doesn't make a huge difference either. You can take any kind of unit with any kind of reason whatsoever, and you get exactly the same number. So I'm not going to worry about units here. That gives you the total phase space size. And the universe as we find it now is some smaller region, and the universe at the Big Bang has to be an even smaller region. Now, I should warn you that this diagram is not drawn to scale. And we'll see a little bit more about this in a minute. But I think I want to say something relating to this question of why it's reasonable to take the black hole as a measure of the available entropy, and why it should be regarded as a maximum entropy within reason. And let me say then something about the second law of thermodynamics. Well, that's what I said before. It's telling you the entropy increases with time, and that entropy is roughly a measure of disorder, but really more precisely it's this volume of the coarse-grained, the volume of the region in that phase space region that I was talking about, the coarse-graining region. Now, I want to talk about a very simple situation that people usually start with when they talk about thermodynamics, the gas in a box. Now, just considering three situations here, the gas may be pretty well tucked in one corner, and it may be sort of spreading away from that, or we might have thermal equilibrium. And time increases and entropy increases in the same direction. So if you manage to shut it off in the corner and you released it, it would start to spread out over the box, and that represents an increasing entropy. Now, if that wasn't just gas in a box, but suppose it was gravitating bodies. So these things, it looks very much like that picture, but these are meant to be a lot of things running around, acting upon each other according to gravity. And if you started out like that, you would tend to find that they can clump and clump more, and finally kind of fall into black holes and things like that. And notice that the arrows I've got are in the same direction. This is increasing time. It's also increasing entropy. But it doesn't look much like the top picture. So this is actually an important point, because although the second law is not going to be violated by gravitational interactions, the effect that it seems to have when you look at it is really almost the opposite. So these things tend to clump. And this is a feature, basically, of the universally attractive nature of gravity. Well, there are other things which may be attractive for a while, but gravity is really the only thing which keeps on being attractive all the time. And there's no stopping it, and that's why you end up with these black holes representing maximum entropy. So that's a useful picture. It also goes some way to explaining this sort of seeming paradox that I think used to worry people, because the Big Bang, as far as we can see, is a very smooth and regular thing, and that people would tend to think of as a high entropy state. Okay, I did say the matter was in thermal equilibrium. That is a high entropy state. But the thing is, as far as gravity is concerned, that's a low entropy state. So the Big Bang was something which, as far as matter was concerned, yes, that was high entropy. But as far as gravity is concerned, it was low entropy. And when the amount of mass gets large enough, that low entropy aspect of gravity is the dominating feature. Okay, well, that's interesting, but you might say, well, what's it got to do with the entropy that one considers in everyday affairs. You stir your teacup and the sugar and the cream get all mixed up and so on, and that represents increasing entropy. What's that got to do with black holes, you might say? Well, it actually does have something to do with black holes, but rather indirectly. So I want to try and indicate what's going on in the Earth with entropy increase. Another thing people worry about is the fact that life, for example, you say, doesn't that violate the second law of thermodynamics? Things get more and more organized and not less organized. Well, you should really understand that in the context of the Earth. Well, you see, it gets something from the sun. If it weren't for the sun, we couldn't have life. And the usual thing people say about the sun is they say we get energy from the sun. But energy is conserved. So as far as the Earth is concerned, as much energy goes back into space from the Earth as comes in from the sun. So it's not the energy, basically, that we're making use of, because it all goes back again. But the energy has a very different form. And the point I should stress here is that we don't take advantage just of the sun being there, but of the fact that the sun is accompanied by the dark sky. If the entire sky were illuminated at the temperature of the sun, it would be totally useless to us. But we don't. We're more fortunate. We have a bright spot here, which is the sun, accompanied by a dark sky. And that represents an entropy imbalance. And if we go back to basic quantum mechanics, you see the temperature here is much higher than this. And this tells us that the individual photons here are of greater energy than the ones that go back again. That means there are far more which go out for the same energy as come in. So although you get the same energy going out as coming in, you get far fewer photons coming in as go out. And this corresponds to a much smaller phase space volume, much smaller number of degrees of freedom, than go out again. This is a large space volume here and a small one here. So that is telling us basically that the energy as it comes in a low entropy form. It goes back again in a high entropy form. So it's the entropy basically that we're taking advantage of the fact that there's an entropy imbalance out there, or there's a low entropy if you like. The sun is a hot spot in an otherwise dark sky, and that is what's keeping us alive. And I've just tried to indicate that in this cartoon. You see, the plants very cleverly take advantage of the sun there and use photosynthesis, and they build up their structure, and then plants may sometimes get eaten by animals, and we may eat plants or animals or what have you, and that's what keeps us going. And what keeps us going is not the fact that we gain energy. That's not much good. You just get fatter and fatter. That's not the point. The point is that you actually lower your entropy all the time. Keep it down. I mean, it's going up naturally because of the second law, but you've got to push it down so that it doesn't go up out of control. Okay, so that's really the point of all this. You keep it down, the entropy you keep down by absorbing a few, relatively few high energy photons and emitting many low energy photons. Now the key thing, as I just said, is that the sun is a hot spot in a dark sky, and the important point is that the sun is there at all. So why is it there at all? Well, it's there because it clumped out of a previously uniform distribution, and because it was there as a uniform distribution, you have the potential to clump and therefore make use of the available low entropy in the gravity which is out there. And that's sort of how we do it. So that little story is to explain how it is that we make use of the fact that the initial universe was very uniform and therefore gives you the potential for this clumping, which gives you these hot spots in the sky. There's all sorts of other complicated physics to go on, like nuclear reactions and this and that, but the important point is that the gravity is there to hold the sun together, and that it's obtained that potential out of the previously uniform distribution that represented the low entropy of the initial universe. Just to give you some feeling, although these models are not the favored ones these days. I've just indicated, I think it's useful to start with this, to consider a closed universe which is also closed in time. We now believe that there is a thing called lambda, which is either called dark energy or else called a cosmological constant, which tends to make these universes keep on expanding. I'll show you some pictures in a minute, but I really want to show you this picture at the bottom. This is for the closed universe. It's not a very good picture because this is meant to be the Big Bang, and people tend to think of the Big Bang as sitting there in some space out there, which you've got to think of the Big Bang as all of space. And so there's nothing outside that Big Bang, but never mind about that. It's the best I can do with this picture. Here it expands, starts off being uniform, and then starts to clump, and then you get these stars and galaxies and so on, and then finally you get this disaster with the whole thing coming back together and crumpling up. And all the time entropy is going up. And although it isn't quite a black hole here, it's the congealing of large numbers of black holes. These red lines here are meant to represent the singularities of black holes. You have this space-time singularity here, which is the Big Bang, but you have, and that's a very neat and organized singularity, and then you have this great mess, which is the congealing of all the black holes. And, okay, well, it doesn't have to collapse. You can have open models. You still have the singularities in the black holes, and they are still complicated. They're not this great mess that you have, which is all-encompassing, but nevertheless, they're still a great mess. And the Big Bang is a low-entropy singularity, and all these things are high-entropy ones. But it's related to this clumping of matter that's going on all the time. Now, I want to do something about estimating how big these sizes are. I had this picture before, and perhaps I should go back to that, which was this one here, and say just a little bit more about that picture. This is a very crude phase-space picture, well, volume estimates, assuming the 10 to the 80th value for the total mass. And here we have the entire phase space, and you have to think of that as something whose volume is, in any old units you like to choose, of reasonable character, of volume 10 to the 10 to the 123. That's the number you get out, as I indicated here, if you use the Bekenstein-Hawking formula with the 10 to the 80th baryon universe. And how big is this region? Well, this is the size of the phase space corresponding to the universe now, more or less. We don't really know these things, but the major contribution to the entropy in the present universe appears to be in black holes in galactic centers. People used to think that it was in the cosmic background, and I've done the red one here is the radiation and matter at the time of decoupling. That is basically the cosmic background, and the entropy there is something like 10 to the 88, and so the phase space volume is 10 to the 10 to the 88. The phase space volume, so if you like, that is what people look at when they look out at the cosmic background. They're seeing a universe whose entropy was something like that. The special region, the entropy has been increasing ever since, mainly in the formation of black holes in galactic centers. The Big Bang, no doubt, was something smaller still. If you believe that the second law of thermodynamics still held prior to that, and Eddington would tell you you have to believe that, then the phase space volume occupied by the Big Bang, the volume, the coarse graining volume, would have to be smaller than these sizes I've indicated. Now, I just want to make a certain point here, which is I did make in the first lecture, something of this nature, perhaps not quite this point, but I'm just trying to say that all you have to look at basically is this top number. In fact, if you try and divide one of these numbers by another, in other words, if you want to find out what proportion is this orange volume of this whole volume, Well, it's 1 in 10 to the 10 to the 123. The size of this thing doesn't make a hoot of difference. It's just showing you how incredibly special the universe still is, if you like. What about the earlier stage here? You divide this number by 10 to the 10 to the 100 to the 88, and it's still 10 to the 10 to the 123. It doesn't make much difference, you see. This number at the top sort of dominates everything. Well, this tells you, the way I like to think of this is, suppose you imagine the creator trying to produce a universe by sticking a pin somewhere in the phase space of possible universes. Well, that creator has to aim for a point. It doesn't actually make, well, you see, that creator has to aim for a point which is accurate to 1 part in 10 to the 10 to the 123. Okay, that seems to have been what happened. But you might try to give all sorts of reasons for how accurately that was done. I prefer to take an attempt at a scientific attitude to this. Other people might think of it in a different way. But at least there's something extraordinarily precise about what went on at the early universe. You can apply the argument down here too. This is saying how special was that in relation to this, and that's 10 to the 10 to the 101. But the reason, I mean, this argument is really, or this picture, if you like, is really trying to show you, and again, I should say not drawn to scale, you see. I mean, if you actually drew that, you wouldn't see any of these others. They'd be so fine, there's no chance of seeing where they were. So you can't do anything but draw them not to scale. And this is telling you the kind of precision that is involved in the Big Bang, or was involved in the Big Bang. Now, I think I'll just give you a version of this argument again, because it's, I think, worth repeating. Here we have the phase space of possible universes again, and the Big Bang is some little point down there, up here somewhere. And one thing I'm trying to indicate in this picture is that these phase space volumes take a little while to get bigger. So if you get close to here, the things nearby are also pretty small. Now, suppose we take what we see of the universe now, and that's this yellow region there. So that's us now. And we want to know what's the most probable way that this could have come about. Well, you see, this is meant to be the history of the universe. That's what that wiggly line is meaning here. We don't know what it is in detail, but it's a general qualitative argument. This is now. This is the beginning there. And if you just constrain now to be in this yellow region that we happen to see, well, what you get is something like this, where whichever direction you go from now, the phase space volumes get bigger and bigger, and well, it doesn't tell you. It's a pretty implausible kind of setup. According to the second law, we know that the entropy must have got smaller and smaller, and in fact this initial state must have been in this very tiny region occupied by the Big Bang. So that's the picture as it was, or is, and is going to be. Well, I should say a little bit about cosmology, because that's of great relevance, you can see. And I'll start with showing you what used to be the standard pictures, the standard Friedmann cosmologies with this thing lambda, which now cosmologists believe is not zero, but the original Friedmann models took the cosmological constant to be zero. You can either call it the cosmological constant or you can call it dark energy. The difference is that if you call it dark energy, it means you think there's a good chance it might be changing. If you call it the cosmological constant, it probably means you're an old-fashioned cosmologist like me who thinks that it's been there in cosmology and there's no big mystery about it. It's been sitting around for all this time and people have just rediscovered it. They've seen what the value is and it's not zero. Okay, that's a perfectly good possibility. On the other hand, maybe it is changing, and maybe we shouldn't call it something which has got the word constant in it. But that's an issue which is not resolved yet, and Maybe it will be at some stage. But as far as I understand it, the evidence is completely consistent with it being constant. However, it's not so easy to make it zero, although I think there are models which people have presented which even allow for it being zero. So it's something you have to just wait for a bit before it becomes clearer. But anyway, these particular pictures have to do with zero cosmological constant. And then there are three of them, three models. There's the case where you have flat spatial geometries expanding with time. Time is going up in all these pictures. So I tried to draw these to look like Euclidean planes, expanding, or they could be closed up, basically spheres, three-dimensional spheres closed up, or they could be negative curvature universes, what are called hyperbolic models. The negative curvature is perhaps the hardest one to visualize. It's the one that mathematicians like the best, because it's a very rich kind of geometry. It's the one I happen to like the best too, but that could easily be a prejudice. What's nice is that the graphic artist M.C. Escher illustrated this in a beautiful way. You have to think of this as a model of the kind of geometry that's going on here. Of course, its space is 3 dimensions in this picture, and the Escher picture is only in 2 dimensions, but you can push that up to 3 dimensions. That's not a big problem. What you have to bear in mind in this picture, although it's a Euclidean representation, it's supposed to represent a non-Euclidean geometry. You see, it's made of interlocking angels and devils, and what you have to imagine is that the devils, wherever they appear in this diagram, are all the same size and shape. They're all congruent. So although they don't look it, that's because there's a distortion in representing the geometry in the Euclidean plane. But you get some feeling for what it's like. And this circle on the outside, which is really a sphere, it's a sphere in the actual geometry here, represents infinity in the geometry. It's also nice that Escher represented all the other ones as well. So we have the 3 basic geometries, although in 2-dimensional form. Here's the flat one, angels and devils again, and there's the sphere. So he did all these 3 things. I should turn that upside down, I think. K represents the curvature, the spatial curvature. You might think, how could he manage to do the same lattice with getting all these 3 geometries? Well, if you look carefully, you see it's not the same lattice, because here you have two devils coming together and 2 angels coming together at that point with their feet, whereas there are 3 here. So it's carefully done. And then there's something else that's different with the sphere here. So it's a very pretty, very remarkable way of illustrating these 3 geometries. But that's worth bearing in mind, because we still don't know which of these it is. If you read the newspapers, you probably think it's this, or if you read a lot of scientific papers, you might think it's this too. But the trouble is that if it's close to being this, and very close to being this, you still don't know. If observations clearly said it was this one or that one, then that would be fine. You'd know it was positively curved or negatively curved. But if observations seem to be indicating it's flat, that doesn't resolve it. It's one of the most pessimistic conclusions. A lot of people like it, but it seems to me a bit pessimistic, because you still don't know which it is. I'll come back to that issue at the end of the talk. But before doing that, I ought to be a little bit more realistic about my cosmologies. And first of all, let me, in fact, introduce this cosmological term, which does seem to be present. And let's say it's there. Well, the main difference is that rather than having the models which collapse, like the positively curved case up here, where you have a big crunch as well as a big bang, we seem to have got rid of that. That's to say, they expand and they tend to go on expanding indefinitely. You can even have versions which don't have a singularity, but that would create more problems than it solves. So the universe seems to be one of these here. You could also have ones which do have a big crunch, but they involve well, these are negative curvature models in these. It seems to be the universe is one of these models. But this isn't realistic yet, for the good reason that I haven't introduced any perturbations. This is actually assuming that the universe is completely smooth, regular, whereas we know it's not. It has irregularities. And these irregularities tend to produce these black holes, which I indicated before. I'm not going to go into that in any detail here, but you can have collapsing stars, which produce black holes, and you can have big regions in galactic centers, which seem to be occupied by black holes. So these black holes seem to be there. There's now some pretty good observational evidence for them. So what we have in our picture is singularities in the future as well as in the past. Now, as I said, we probably have a cosmological constant or dark energy or what have you. So these are probably the most accurate pictures. I can't say that my drawings look terribly accurate, but that's qualitatively an accurate picture of the universe. Which of these three it is, of course, is the issue about the spatial curvature, which I do want to come back to briefly at the end. Now, the point that I've been trying to emphasize here is the very special nature of the Big Bang. And there's a real paradox here, if you like, because if you have a theory which is supposed to explain the nature of the Big Bang, and that's one of the reasons people try to do quantum gravity, try to combine gravitation theory with general relativity or gravitation theory, quantum mechanics with gravitation theory, that one of the aims would be to make physical sense of what's going on at the singularities. But you see, you have something quite different to do here from what you have to do here, because the Big Bang singularity seems to be this very low entropy, smooth singularity. The singularities in gravitational collapse, the black hole singularities, are very complicated and not anything like, in detail, the initial singularity. So if you're trying to have a theory which explains these, well, which theory will do it? And what are the various theories of quantum gravity? Well, I mentioned strings, or M theory, in the first talk, and I also did refer to the loop variable approach in the survey that Carlo Rovelli did, and there's also the Hartle-Hawking no-boundary approach. And the thing is that all these approaches use standard quantum mechanics or standard quantum field theory. And the ingredients that go into this are all symmetrical in time. And it's very hard to see that you can get an asymmetrical, a really profoundly asymmetrical conclusion from theories where the input is completely symmetrical. So this is one point. And another point is that those who do try to use quantum gravity to understand singularities, the usual thing they try and do is to say, well, they get rid of it. And they say there isn't a singularity. There was a prior state of the universe which collapsed inwards and didn't quite become singular because of quantum gravity effects, and then exploded out again. So this is the kind of model that people often try to produce, something which collapses and then whoomp, goes back out again. To me, this is basically misconceived. See, most approaches, to the extent that they address the singularity problem at all, would seek simply to eliminate the singular state to achieve instead a bounce. Now, the problem with doing this is that you've made your life worse than it was before, in a sense, because the problem of making an initial singular which is special is hard enough, but if you somehow manage to get rid of this place where you might well expect new physics to take place and replace it by a collapsing state, that collapsing state has to be focused somehow on this extraordinarily special singularity here. And it's much harder to believe that you could plausibly produce a model which aims itself so accurately that you get this 10 to the 10 to the 123 precision, where you don't have anything special. You see, when it's coming in, it's just ordinary physics. And why should that ordinary physics contrive to produce this very, very special state. So in my own view, to eliminate the singularity is basically misconceived. Even if successful, such a program would abandon the best hope we have of resolving the mystery. And I say it's a mystery, despite what Eddington said, there is a profound mystery in the second law. It's not something which sort of is automatic. There's a puzzle, and the puzzle is only right at the beginning. From there on, if you like, it can be understood what's going on. But right at the beginning, there's a very profound puzzle as to why it has this extraordinarily precise organization. Okay. Now, where are we? Oh, here they are. At this point, I ought to say something then about inflation, because this, I haven't put any inflation in these pictures here. It's something which has become almost standard cosmology. If you buy any book, pretty well, I should think, popular book, which is at least reasonably recent book, you'll find that in the early stages of the universe, there is supposed to have been this phase known as inflation. And that is supposed to explain the problems that one might think about to do with the Big Bang. Well, what's inflation? I'm afraid my pictures, of course, are not terribly to scale or not very accurate, but I'll do my best with them. This is the issue of inflation. And here we have the Big Bang here. And the idea is that prior to the time, if you like, when the cosmic background radiation, that's what people refer to as the flash of the Big Bang, and that's what people look at with these wonderful new experiments, well, initially COBE and Boomerang and the WMAP, all these wonderful, very good experiments which measure the cosmic background radiation, still what's left of the flash of the Big Bang, but that's supposed to have been after some other expansion which took place by some enormous factor. There seem to be different versions of inflation involving different factors, but this is an exponential expansion which is supposed to have taken place after the Big Bang. Now I'll try and explain why people wanted to do this, and from there on we had the ordinary cosmological expansion. Later on there may be another exponential expansion which is due to the cosmological constant, or the dark energy. But the picture, I'm afraid, not a very good picture, something like this. I've said the expansion factor may be something 10 to the 60, but sometimes people have said much bigger figures and sometimes smaller ones, so I'm not going to worry about the exact value. Now, why did people think this was a good idea to introduce inflation? Well, there were at least 3 problems that this is intended to resolve. Well, I've listed them here. I'm not sure if I've said them quite the way people say them, but there's the thing called the monopole problem. I'm calling it the temperature problem. I think it's called something else, but I couldn't remember what it was, so I'm calling it that. And the flatness or smoothness problem. Now, the first one was actually the original reason for inflation, and I don't want to go into that particularly because it's not necessarily relevant. It had to do with certain what are called grand unified theories, or GUT theories, which predicted the existence of certain things called monopoles, and nobody could see them. So the question is, why aren't they there? Well, one reason they aren't there might be that this theory is wrong, but another reason is that if they should be there, maybe this great expansion that took place kind of made them rarer and rarer, so that you are not likely to find them in your neighborhood. And that was the idea there. It seems to be a perfectly reasonable way of trying to explain why the monopoles aren't there, but not a necessary one, because they maybe weren't there in the first place. But the other ones are more serious issues which seem to apply whatever view you might take of the microphysics of the world. And one of the issues here then, that's what I call the temperature one, is why do we see so very closely the same temperature when we look at 2 separated regions of the cosmic microwave background sky? So you look over there, and you look over there, and you see the temperature, slight variations, and that's what people measure, but basically the temperature is the same. And this seems to be an extraordinary thing. Why are the temperatures the same when they could have been completely different? And worse than that, if you take the standard picture of cosmology, and what I've done here is used a conformal diagram. It's actually a very useful way of talking about cosmology. Time is going up the picture. Here's us now. And what I tried to do is draw the model where the light rays are represented as going at 45 degrees. That's just a very convenient way of doing it. And you might have to stretch or squash your picture one way or another, but it's a convenient way of doing it. And the Big Bang itself is this red line here, which I've stretched out. You might have thought the Big Bang was a point, but in this representation, it's a great big spatial region there. And the origin of the cosmic microwave background is just a little bit ahead of that in time. And as we look back, here are two regions of temperature that you might be looking at. And you say, why is it that these temperatures are almost the same? When, if you go right back to the Big Bang, you're looking at what could have caused this temperature and what could have caused this one. They're two completely causally disconnected regions. There's no way this could have influenced this or this, that. So it looks like a miracle that the temperatures are the same. Now what inflation does, and I won't explain in detail why it does that, but this is what it does do indeed, is that the Big Bang is pushed back. This region of exponential expansion has the effect in the conformal diagram of pushing the Big Bang not from up to be up there, but way down here somewhere. So that these two regions, which seem to be causally unconnected, disconnected, are in fact overlap. And the claim then is that whatever the temperatures were initially, because they overlap, they were able to thermalize and become equal. And that's the reason that the temperatures are pretty well equal. Now, that's one reason. And then there's the flatness one. Let's just see what order my transparencies come in so I don't get myself confused. Yes, the other one then has to do with why the universe seems to be so uniform and flat. And the claim is that, sort of more or less, no matter how it started, you could have a Big Bang which was somewhat complicated, but there is this inflation effect which has to do with some scalar fields which are introduced into the physics, and they cause the universe to undergo this exponential expansion, and you suppose that there's at least a reasonably smooth region to begin with, but not particularly flat, and because of this enormous expansion, it's stretched out to something which is pretty well uniform. So those are the two reasons, if you like, initial motivations for studying the inflationary models, that they seem to do these two things: allow the temperature problem to be resolved and allow the flat picture, or pretty well close to flat picture, to arise. Now, I want to try and argue that neither of these is correct, that they just don't work. The first point is just to think about what thermalization does. See, what is thermalization? It means that you have two regions here, and in effect you're connecting them. Remember, in my first transparency I had a hot and a cold body, and I joined them with a conducting rod, and that means you are now bringing them into causal contact, and the temperatures become equal. And that's what's supposed to be going on here. You're saying initially they may not have been equal, but they thermalized. This is basically the connecting rod which makes the temperatures equal. But if the temperatures become more equal, well, this is a thermalization process, and that means that the entropy has gone up. Remember, I said this is an illustration of the second law. If you have unequal temperatures and they become equal because of a connection, that is the second law in action. The entropy has gone up. Now, what I'm trying to say is that the problem, the real problem you've got to explain isn't, these are just sort of two instances of it. The real problem has to do with why the initial state was so special. Now, if you're trying to pretend there isn't a problem there and say that, okay, the temperatures being equal is due to thermalization, you've actually made your life harder, because what you've done is to make the state, which is actually a more probable state, out of a less probable state. So if you're trying to say that thermalization has made these temperatures equal, what you're saying is that they were perhaps unequal originally, and therefore the entropy was actually higher. It must have been higher when they were unequal than when they're equal, because otherwise when you joined them the entropy wouldn't have gone up. So this is telling you that the problem you have to address of why the universe was so special is actually worse. And you haven't addressed it. So the point is you're touching on issues which have to do with the nature of the early universe without really addressing them. These are small fry. You're not touching this 10 to the 10 to the 123. You're addressing some minor problems, and in fact, in the process, making your other problem worse. Okay, well, that was one of them. That's the thing I said here. The thermalization increases the entropy, therefore the state must have been even more special before than without thermalization. So the problem is made worse. Another way of saying that is it's actually a more probable state that those two temperatures should be equal than they should be unequal. It's a bit hard to imagine that. You think, oh, well, it's an amazing piece of fortune that they're equal. But you imagine joining them with a rod, and then they become equal by thermalization. So you've become a more probable state after than before. It's something that needs to be thought about, maybe. So anyway, let me leave it at that. The other question is, what about this expanding out to produce a uniform state? Well, you might think there's something a bit fishy about this anyway, because you're trying to produce a state which, from the gravitational point of view, is low entropy out of something which is high entropy. And that's really basically the problem. Again, one is trying to produce something which has low entropy by starting with something random. I should say that inflation is not the first time people have tried to do this kind of thing. There's an older family of arguments known as chaotic cosmology, where people, this is quite a long time before inflation, where people tried to explain why the universe had the regularity that we see by introducing other different kinds of thermalization processes. And so they're saying, well, you start off with something random and then somehow it becomes what we see. But what I'm trying to say is that's basically misconceived, because you've got to have a second law of thermodynamics. And the second law of thermodynamics says that the earlier state was particularly special, and if you introduce thermalization, you're just making your problem worse. It's the same argument as I was just giving a moment ago. But what about this argument here? Now, in the first place, it's not at all obvious that it's going to work. If you bear in mind that this singularity here is likely to be something very complicated. Indeed, it's even quite likely it's what's called fractal. Now, fractal states have the property that if you expand them out, they look just as bad as they did before. And if it were fractal, indeed, this expansion process wouldn't give you anything smooth. Now, you might say that, well, that's pretty unlikely, isn't it, that they should be fractal? But it's not at all unlikely. And the type of argument that one can use to justify a picture where, if not fractal, even probably something a good deal worse, is really to consider the time reverse of a universe, maybe a closed one. I had a picture earlier on of doing this, which I'm not sure I can lay my hands on at the moment, but it doesn't matter too much. If you consider one of these singularities of collapse, they're likely to look like a great mess. And the thing is that your universe could be anything. Just imagine now time reversing, so we're looking this way now. So whatever it is, you choose your universe to be anything, whatever kind of mess you like, and then extrapolate this way. That is to say, this is a collapsing universe now, and then it'll produce something which, if you now reverse time, would have given you whatever you started with. So what I'm trying to say is that even if it's not fractal, but something else, it's probably something worse than fractal, it's the more general state to be something complicated. Let me leave the argument at that point. But basically, what I'm trying to say is that the main motivations for inflation seem not to work. It doesn't mean inflation is wrong, and I should make this point here. It might turn out that inflation is actually the right theory, but that it's sort of reasoning, come about from reasoning which is faulty. Well, we know good examples of this, actually. I mean, even one of the most famous was Dirac's discovery of the equation for the electron. And in this, he made an assumption that the equation governing a quantum particle should be a first-degree equation, a first-order differential operator. And he was then led to this beautiful equation, which does actually describe electrons in a magnificent way. But later on, people found that you didn't need that, and you could have other kinds of particles which are described by second-order equations and scalar particles and so on. But there we had an example where reasoning, which was not really completely correct, gave a beautifully correct theory. So it's conceivable that that's what's happening here. So I just feel I should make that point because it's certainly not telling us that it's wrong. But it does, in fact, remove some of the main motivations. Now, in fact, really the main motivations. Let me try and say something else here. You see, the sort of thing people tend to say about inflation is that, okay, maybe there was a great mess at the beginning, but then most of these things didn't inflate, or they didn't produce universes that anybody could live in. But maybe one was lucky, and there was a little smooth bit here which expanded out and produced the whole universe that we know. And the reason that that works, okay, most of these things didn't do that, but we're here, and since we're here, we've got to be in a congenial universe. And so there might have been other parts of this great multitude of possible universes which didn't do this, but there's nobody in those universes. So this is a version of what's called the anthropic principle, or the anthropic argument. And I think it's worth addressing that here, because I think one has to do that in connection with inflation if you want to try and maintain this kind of argument over here. If one was trying to make out that a generic universe could give rise to what we see. So this is the anthropic argument. But the main problem with the anthropic argument is that, well, in this context I should say, is that most of the universe we don't really need. I mean, all we need, I don't know whether we need the whole galaxy, for instance. We certainly don't need it to keep on going onward, on and on and on. When people look out at the sky, at the universe, they see it keeps on, keeps on, keeps on, keeps on. Now, you see, it might be that just a little bit of this, see, I've got a picture here which is indicating a large region of initially smooth universe which is supposed to expand out by inflation and give us a universe that looks special. You get this degree of specialness of 10 to the 10 to the 123. But you see, I'm saying we don't need all that. And I'm going to be very generous and say, suppose we actually needed out to 1/10 of that distance. I mean, I don't believe that, but suppose we needed out to the 10th of that distance. Well, that's only, instead of 10 to the 80 baryons, that's only 10 to the 77 baryons. So to produce that kind of universe, we don't need this much specialness. You hunt around until you find only the one that needs to expand out by this much, well, by a much smaller factor, which gives us specialness of only 1 to the 10, and 1 in 10 to the 10 to the 117, which is what you would get for 77 baryons. And the thing is that it's enormously more probable. So you get a much smaller number, 10 to the 10 to the 117, instead of the 10 to the 10 to the 123, which is hugely smaller, in fact, by the factor, as I did before, of 10 to the 10 to the 123. So this is pretty expensive for making this hugely unnecessary region for us. You might say, well, the bigger region is really better because you don't just get us, but you get copies and copies and copies and copies, many more of them all over there. But this is a very expensive way of doing it. It's much cheaper to do it again and again and again and again. You get that many people. You don't have to produce one connected region to produce the universe we see. Well, I don't think I should follow these arguments too much. But what I'm trying to say is that the anthropic argument, which is this one which says, well, we're here and therefore have to see this much specialness, that anthropic argument doesn't wash. In fact, I don't know how much specialness we need to make people, but you could certainly get away with 1 in 10 to the 10 to the 60 just by random collisions. You see, you just say, suppose you wanted to produce the solar system as we know it by particles coming in randomly and assembling themselves into this solar system with everybody in it. You could do that with an improbability of something like 1 in 10 to the 60. And therefore, well, 1 to the 10 to the 10 to the... Oh, getting confused here. The improbability of 1 in 10 to the 10 to the 60, which is utter, complete chicken feed by comparison with the way it was apparently done. So it wasn't done for our purpose. It wasn't done just for us, is what I'm trying to say. It was there for some other reason, which one would like to think is something to be understood in terms of physics. And it has to be a physics which is beyond the kind of physics we know. I'd like to just end with a few more comments, one which relates perhaps some of the points I was making today with some earlier arguments. One has to do with, you see, inflation, if it were just these initial motivations, probably inflation wouldn't be so popular today. But it does make a good stab at explaining the actual variations that one sees in the temperature in the microwave background. Now, the argument that's used has this kind of character. What you say is that there were these things called quantum fluctuations which took place in the early universe, and they are basically consequences of the Heisenberg uncertainty principle. They tell you that if you try to measure something, well, the original Heisenberg thing is if you measure position accurately, then the momentum is very uncertain, and vice versa. But this applies also to the geometry or to the scalar field in inflation, and it has the consequence that there is very great irregularities in the early, in the geometry or in the inflation scalar. And the idea is that although these are very tiny, maybe the size of the Planck scale when they are produced, because of inflation they get spread out to huge distances, and these are the irregularities that we now perceive in the microwave background. And using appropriate assumptions, one can make something which does indeed model what's seen pretty accurately. Now, I want to point out that there is actually, in this argument, something which needs something which I was talking about 2 days ago. And the thing is that when we talk about quantum fluctuations, these are quantum things. And it's not that the geometry is something very complicated, but that's one component of a vast superposition of different geometries. In fact, it has to be like that, because what you're assuming is that there was an initial state which was very symmetrical, and somehow you got these irregularities. Well, the irregularities don't come out of a symmetrical state. A symmetrical state stays symmetrical. The quantum evolution, the unitary evolution, the Schrödinger equation preserves the symmetry. But it doesn't necessarily preserve the symmetry in any one of these components. That is to say, you have one complicated, messy geometry superposed with another, superposed with another, superposed with another, such that the whole superposition is symmetrical, but the individual ones are not. So to make this argument work, what you need is some form of state reduction. I call this objective reduction. The quantum state evolves and retains the symmetry it started out with. If you want to break that symmetry to have something irregular, you need a version of the state reduction of the state. Or this is the measurement process in quantum mechanics. Now, there was nobody around when these things were supposed to have happened, so it can't have been ordinary observers. Nevertheless, it might have been some other scheme that one needs for reducing the state. And that seems to me a good place where a new theory of objective reduction could indeed come in extremely valuable. Now, as far as I'm aware, virtually nobody has done this. If you read books to do with inflation, you sometimes find they just skate over it completely and ignore the issue. Sometimes they do address it and say, this is an example of the Schrödinger's cat problem, and then more or less say, well, it's not our concern to try and solve that problem. Well, it is really, because this is a key place in which the reduction of the quantum state would have a very important role to play. In fact, it could be a good test of one's theory of objective reduction. Does it give the right answer? Well, we have now wonderful data in the cosmic background radiation, and does it give the right answer? And in fact, there are some people at Penn State who have made an attempt, I'll just say this is a stab at this, the only model that I know where they've tried to take this seriously. In fact, they do it within the context of inflation. A tentative model by these people, Penrose, Salmon, and Sadowski. But I think it's very early stages. Okay, that's one point. Another point, I should make some comment about models which, to me, seem to me more fantastical. I would say that the inflationary model is pretty fantastical. It's introducing this enormous expansion. It's introducing fields that we have no other reason for believing in physics. But if it really worked, fine. And as I was saying, we do need something very strange to explain this very odd initial state. I don't really see myself that inflation is, if you like, isn't strange enough. It involves physics which is time symmetrical. It isn't really strange enough. But what about stranger ideas? And I shall refer to this model which has been put forward at least partly here, the thing known as the ekpyrotic model. And this involves some kind of collision by things referred to as D-branes, and here's the crash which causes the Big Bang. And maybe this happens again or what have you. I have a lot of troubles with this. I'm only mentioning it quickly here because it's a nice example of what I would call a fantastical model. One of the troubles I have with it is it assumes already that the things I was talking about on the first lecture are correct, that string theory is right, and that the M theory ideas which come out of string theory are right, and that there's these D-brane things. I hadn't even tried to explain what they were, but they're part of the theory, and that they're there, and you have higher dimensions, and so on. So there's an awful lot of assumption going into that, most of which I think is pretty dubious. Moreover, it's trying to do something which I indicated was basically misconceived about the Big Bang, trying to get the Big Bang out of a previous collapse. Okay, it's a different kind of collapse, but it suffers from the same problems. How is everything geared so very, very precisely to produce this 10 to the 10 to the 123 sort of thing in this resulting universe that comes out of it? There's no attempt at an explanation of that. So to my way of thinking, it doesn't, whatever other things it might try and explain, it doesn't even attempt to solve what's the big problem of the early universe, why this state was so extraordinarily special. I think that this needs some new quantum gravity theory in which the quantum mechanics is time asymmetrical and where the reduction process is something which is objective, the OR idea that I referred to. So we're probably a long way from that, but I would personally think that's the right kind of route to follow. Maybe someday we'll have an explanation for these things. Now, I could mention one thing here. I remember this, I used this in the early lecture here. I had this pointed out to me. I don't think I'd known this when I put this up before. And I'd mentioned sometimes old ideas come back again. There's a sort of irony here that the Platonic view of the cosmos, if you like, was this dodecahedron. And there's this model that had been recently proposed which suggests that maybe there is a big dodecahedron in the sky, or put it more accurately, the interior of this dodecahedron would represent space, but where you identify opposite faces with a bit of a twist too, and that produces a model which is completely closed up on itself. It's, if you like, a version of the closed model, of the Escher model which I represented here, but where there is some elaborate identification, sort of thing that you might imagine if you tried to identify all the angels and all the devils and that. You couldn't quite do it that way, but it's that sort of a thing. I only mention this because it's a bit of an irony that this example here, which was been suggested so long ago, has now already come back in some form. It seems almost certainly it's not right, but it would be rather pretty if it turned out to be right. I finally just want to make a comment about my own prejudices here. I did mention something about twistor theory, really only in the Carlo Rovelli's counting of numbers of papers, which in different quantum gravity ideas. I think perhaps I should say this just because I've been talking about other things which haven't referred specifically to that. You might ask the question, does twistor theory have anything to say about any of these questions? Well, it does, but not very much. It has something to say about string theory and so on extra dimensions. It says that space-time should have 4 dimensions. This is one of the reasons, just to show you that there are additional reasons to the ones that I gave for being doubtful about higher dimensions. And it comes from twistor theory. I don't need that picture, so let me take it away because it's confusing probably. It really has to do with the nature of the celestial sphere. If you look at the sky, you see a sphere out there. And twistor theory is really based on one way of representing that sky, and that is in terms of complex numbers. And it's a very beautiful way of getting the right transformations of relativity theory from the view that that sky is best described in complex numbers. Now, that only works if the number of space and time dimensions is 1 time and 3 space. And I always thought that was a positive aspect of this because we seem to have 1 time and 3 space. But people nowadays talk about higher dimensions, and one has to think whether that really will hang together. It also has something to do with what I said in the second lecture, because it relates to some kind of nonlinear generalization of quantum mechanics. What one finds is that the description of gravity, the quantum description of gravity, is something nonlinear. It doesn't get terribly far with that, so I don't want to make a big thing of it. What does it say about cosmology and the Big Bang? Well, it's only suggestive and doesn't really say very much. And what it is suggestive of is that the correct model ought to be this one. And the reason it says that is that you want to have a very special initial state in order to get something with a chance of resembling the universe we see. Inflation won't smooth it out, I say, but if it started very symmetrical, then maybe that's what it did, and that the irregularities came about indeed because of some sort of state reduction, and quantum fluctuations or that sort of idea could easily come about if we understood about state reduction. But if you have a very special initial state, what initial state is it likely to be? Well, it could be one with any one of these symmetries. Now, the thing about these symmetries is that this one here is the only one which has a symmetry which can be described naturally in terms of complex numbers. Basically, it's, if you think of the sphere, that looks like a circle around the outside, but in 3 dimensions it would be a sphere. That sphere is something that you can understand in terms of these complex numbers. It's a conformal sphere and so on, and it's the same sphere, if you like, as you see when you look out at the sky. And that only works if you take negative curvature. So I've always been rather favoring of this model without any, and it's prejudice, if you like, There's no observational input from that. Now, observations seem to have been saying that we have a flat universe. Well, people who take the dodecahedron, well, thinking it's a positive curvature universe. There are dodecahedrons which give you the negative curvature one too, I should say. So if it really was a dodecahedron, you could fit it either way. It might be one of those or one of those ones, but it couldn't be a flat one. Now, people do this analysis of the cosmic background, and the way they do it is to analyze that sphere in terms of what are known as harmonics, or spherical harmonics. And that is a very good procedure for analyzing things. So especially if you had a balloon and you wanted to know how it oscillated and so on, you'd describe it in terms of those harmonics. And that's what people do, and they look at the very high harmonics and they find the little tiny ripples are very much in agreement with the sorts of model, the standard kind of model, which is in accordance with the inflationary picture. Doesn't mean that that's right, but at least it seems to be in agreement with that. There are a number of things you might fiddle around with there to make it better or worse. But these harmonics work very well for the high ones, but when you look at the low harmonics, that is the big oscillations which involve the whole universe, you find there are some discrepancies. And in the recent data, there seem to be some discrepancies at that level. And this is one of the reasons, in fact, that the people who like the dodecahedral model made this suggestion, because to try and explain these discrepancies. Now, I may say I'm not really up with the different ways you might try and address these discrepancies, but one of the ways seems to be not to have a positive universe like with the dodecahedral model, but you can also do it with the negative one. So it is possibly an indication that we do have negative curvature. I think it needs more observation to see whether that's right. Certainly the scale is huge. The observable universe would only be some region fairly much in the middle of this big region here. There's one other piece of evidence which I've known about from some time, but it's not been very much publicized, and I don't quite know how to take it. This is due to a theoretician known as Gozadjian, and he has done a completely different way of analyzing the cosmic background radiation. You don't look at multipole moments. See, if you just look at the different multipole moments, you lose most of the information. There's lots more information in that data. The data is actually packed with information. And what people do is to draw some nice curve which fits in with certain aspects of the expectations of the early universe. It does seem to do it very nicely. But nevertheless, it's only a tiny bit of the information sitting in that data. And what Gozadjian has done is something quite different. He's looked at the regions of equal temperature to see whether they're kind of spindly and stretched out, or are they fairly kind of round. And his claim is that if the curvature is either positive or flat, then they would be pretty round. That's these two models here. Whereas if it's negative curvature, they should be all stretched out. And he's done an analysis originally of the boomerang, with colleagues, I should say, originally of the boomerang, but now more recently originally of Kobe, but then of boomerang, and then he's looked at the other ones too. And the conclusion is that you do get this stretching out, this ellipticity, which would be an indication that this kind of model is correct. Well, I don't want to give a view on that at the moment. I find it exciting, and I hope these things will be followed up. And maybe within a few years, people are always saying that, and they still haven't. Maybe within a few years, we'll know which of these models it really is. What is the nature of the cosmological constant? Is it really a constant? Is it this dark energy stuff? And even this stuff I hadn't even mentioned, which is the major content, apparently, of the matter in the universe, which is this thing called dark matter. Or maybe that's not there, and there's some other explanation for what people see. So there's a lot of exciting things, and maybe in a few years these answers will be known, or maybe they won't. In any case, it will be nice to see what happens. Thank you very much.
Do you see the fact that the inflationary field violates the strong energy condition as a very serious problem for inflation?
Could be. Yeah, it's. I mean, it certainly does. I mean, this kind of condition is one that has been used in proving singularity theorems, and that's ordinary matter should satisfy these things called energy conditions. And I think inflationary cosmology, there are all sorts of problems of that sort, which I've always had with it. One is, for example, how it knows to turn off all at the right moment and everything like that. When one has a greater, the symmetry that you have originally is de Sitter space symmetry, and how does it know somehow to switch off simultaneously and things like that. So that's just another instance of things, worries that I have about it. So I agree with you. In fact, when I first heard about it, it's one of these, just shows how bad my judgment is, because when I first heard of inflationary cosmology, I thought, oh, that idea won't last a week, you see, and it's been around for many, many years now. But the thing you mentioned is the kind of thing which trouble, if you look in detail with it, that's one of the troubles. But this kind of issue, I think, is also a problem if you think that this dark energy is actually something which can vary. Because if it's allowed to vary, then it's got to have there's another side to the equation, which maybe that's the dark matter or something. And there's a problem with making sure the energy conditions are satisfied in that context. And I think these are serious issues. I mean, it may be, you know, that people don't mind, because in quantum field theory, you can actually violate energy conditions, at least in small regions. And but I agree with you. I think that things of that nature are things which make me skeptical. But I didn't refer to that here. Thank you.